Hi everyone. We will be presenting a Pearl on the type-driven tokenization of Brahmic scripts. We will talk about why standard tokenizers corrupt Brahmic text, and we will also show a machine-checked repair in Agda. Every large language model begins its life with text, massive unstructured corpora spanning billions of words. This is the raw material the model must learn from. As humans, we naturally read this sequence of whole words. For example, nationalization, ionization, tokenization, and so on. But a neural network cannot process raw text directly. Before any training or generation can happen, this human readable text must be translated into a sequence of numbers that the model can actually digest. That translation step is where our story begins. The translation starts with a tokenizer. But modern tokenizers do not just split text at the spaces. Instead, they can scan the corpus for statistical patterns. They quickly discover that certain fragments, like the suffix ization, appear constantly across entirely different words. Rather than memorizing every single long word as a unique entity, the tokenizer extracts these high frequency patterns, turning them into reusable building blocks. These discovered fragments are then compiled into a fixed vocabulary, where every piece is assigned a unique integer ID. So, when we feed the word nationalization into the system, it gets mapped to a sequence of numbers, say 8643 for national and 937 for the suffix ization. Notice that the tokenizer isn't trying to find linguistic roots or understand grammar, it is purely statistical. This brings us to a critical point. Once mapped to an ID, that fragment becomes an indivisible atom to the neural network. The model does not know what letters are inside it, and it is completely blind to the rules of the human writing systems. Now, let's fast forward to inference. When a user interacts with the model, say they type the text flawless token. Because the model only understands numbers, the tokenizer converts these words into their integer IDs. Those numbers then flow into the neural network. The model calculates the statistical relationships and predicts the most likely next ID. Here, it outputs the ID for ization. Finally, the tokenizer decodes that number back into text, yielding flawless tokenization. Now, because the model is probabilistic, it evaluates many possible continuations. If we feed it the phrase the atomic, it processes those numbers and might highly rank the ID for number, giving us the perfectly valid phrase the atomic number. But then, because the model is making probabilistic guesses for that exact same input, the atomic, the model could predict the ID for the suffix ization instead. The result is atomic plus ization, which is obviously invalid English. Ideally, we would want atomization. But here is the crucial observation for our paper. While it is semantically incorrect, it is orthographically perfectly valid. The letters snap together without issue, and the rendering engine does not have any problem displaying. In English, you can concatenate any two valid strings together and get another valid string. But the same does not apply to languages like Telugu. On the left is a single well formed rendered unit, the prefix Vignya, meaning knowledge in Telugu. The word is made of six characters, the properties of which I will explain shortly. Now, suppose a naive tokenizer splits the word after the third character. The right hand fragment begins with a dependent character, a virama, or a combining mark. These dependent characters have no independent rendering. They only attach to a base character to their left. So when a text fragment starts with such a dependent character, the rendering engine can't attach it to anything, and so it exposes the error visibly as a dotted circle. We will now take a step back to review the Telugu language. We will not learn it entirely, of course. We will just go over the five types of characters in the language. We'll start with a consonant. So this carries an inherent vowel, and more importantly, it may start a token. Then we have the independent vowel, which is a standalone vowel. It may also start a token. Then we have the dependent vowel. This attaches to a base consonant and cannot start a token on its own. Then we have the virama. This cancels the inherent vowel of a consonant and also connects consonants. It is also a dependent continuation and cannot start a token. And finally, the vowel suffix. It is a nasalization or aspiration mark. It is also a dependent continuation and cannot start a token. So that's the entire reading guide. We have two starter types and three continuation types. We'll keep the colors consistent throughout the talk so that they are easy to follow. We now revisit the same prefix from earlier, Vignya, but now unpacked into the underlying Unicode code points. Each character is tagged with its type and code point. When we read it from left to right, we have a consonant, a dependent vowel, consonant again, virama, a consonant, and finally a dependent vowel. Notice the two starter types interleaved with the dependent continuations. Now watch what a naive tokenizer does. It places a split right here after the third code point. That leaves the virama at the start of the right hand token. And a virama is a forbidden start state. It is a dependent continuation which can never be a valid beginning. That single mislabeled boundary is the bug we address. The dotted circle from slide 1 is the visible symptom. So the property that was violated is now precise. That is, a token must begin at a valid start state, which is either a consonant or an independent vowel, and never at a dependent character. That's the invariant we'll enforce with types in the rest of the talk. Now let's lift the bug from the previous section into an algebraic statement. For an alphabetic script, concatenation of two valid fragments is total. That is, x dot y is always defined. Any two pieces can be glued. That's a semigroup. For a Brahmic script, that's not true. X dot y is defined only at valid boundaries. Gluing requires evidence that the transition between the two fragments is permitted. So the right structure is a partial semigroup. That is, composition is a partial operation, not a total one. One caveat here, though, is that this is a claim about the orthographic well-formedness, that is, whether the result is a valid sequence of glyphs. It is not about whether the resulting word is meaningful. To make the definition of a valid boundary concrete, we model each character class as a state and each valid adjacency as an edge. Consonant, independent vowel, dependent vowel, virama, and vowel suffix are the states. And an arrow from A to B means a character of class B may follow one of class A. If we trace a couple of edges, a consonant can be followed by a virama, that's what we call a dead consonant. A consonant can take a dependent vowel, and you can always move on to other consonants or an independent vowel. And as you can see from the graph, there is no initial edge into a virama or dependent vowel, meaning no Telugu text can start there. That absence is how we fix the bug from the last section. So the task now is to encode this relation using types. Here we have the transitions in ACTA. First, we have the character classes as a plain data type, Unicode Brahmic. 5 constructors, 1 per class. Then we have the transition relation indexed by a source and a destination class. Each constructor is a proof that one specific transition is valid. Dead consonant witnesses consonant followed by a virama. Vowel symbol witnesses consonant followed by a dependent vowel, and so on. So a type like consonant followed by virama is inhabited. We can hand the constructor dead consonant as evidence. But dependent vowel followed by virama is uninhabited. There is simply no constructor for it. So the most important code here is the code that actually doesn't exist because no constructor witnesses that a virama follows a dependent vowel. That state is just unrepresentable. Now we compose single transitions into a whole token. Valid chain certifies that every adjacent pair in a list is a valid transition. Base for a singleton and step to prepend one more code point given a proof that T2 follows T1. But a valid chain isn't enough. We also need the first element to be a valid start. That's where we use the type valid Brahmic token. Notice that there are exactly two token constructors, consonant start and vowel start. A token beginning with a consonant is constructible. A token beginning with a virama is not. There's no constructor that starts there. So the start state condition from the transition graph is now baked into the type of a token. A value of type valid Brahmic token carries its own proof that it begins with a valid character. Given the specification, we can now write a function that fixes token boundaries. The algorithm is a one character look ahead. The question we ask is, does the remainder begin with a valid start state? That is, a consonant or an independent vowel. If yes, we emit the current token and stop. If not, we absorb that leading character into the current token and recurse. If you look at the fixed token definition, the consonant and independent vowel cases stop and hand back the remainder, while the dependent vowel, virama, and the vowel suffix cases absorb one character and recurse. And it is guaranteed to terminate because every recursive call shrinks the remainder by 1. Given this fixed token function, let's replay the bug in the prefix vigna from earlier. In the top row, we can see the naive tokenizer's proposed split. The second token starts with a virama, which is an invalid start. After applying one step of fixed token, the candidate on the left absorbs the virama. And in the bottom row, we can see that the boundary has moved one place to the right. Now, the second token begins with a consonant, which is a valid start. Nothing else about the text has changed. We have the same code points, same order. We only moved the boundary to the nearest valid position. One step was enough here, but in general, we recurse until the remainder starts from a valid character. Finally, we share the three machine check lemmas that prove the repair. We start with validity, that the repaired token is a valid Brahmic token. It really does begin at a valid start state. Then we have one on the remainder, which is that whatever is left over is also beginning at a valid start state. So the next token can start safely and the invariant is preserved across the whole chain. And finally, completeness, which means no code point is lost or duplicated. The repair is essentially lossless. Put together, the tokenizer is safe, compositional, and lossless, all verified in ACDA. The most direct translation of our ACDA model is to patch sentence piece directly. On the left, the is dependent or combining function is essentially our ACDA valid transition function written in C++. We hook this into the is valid sentence piece function in sentence piece, which is called during both unigram and BPE training to reject any candidate token that starts with a dependent mark or virama. Now we need to make a correction to our paper here. We originally stated that this patch was a complete fix, limited only by the fact that it hardcodes specific Unicode ranges. That is not entirely accurate. Empirically, with a clean corpus and a large vocabulary, this avoids invalid characters. But theoretically, it is incomplete. Sentence piece separately retains single character pieces to guarantee text coverage. Meaning, this filter alone cannot mathematically guarantee that every emitted token starts at a valid boundary. A truly complete fix inside sentence piece would require a massive invasive rewrite of its core logic. So rather than fighting the tokenizer's internals, we took a different architectural approach. And so we built a Rust pre-tokenizer to enforce our rules at the boundaries. First, we take the raw text, like our Telugu example, and apply our transition rules to group it into typed valid clusters. But here is the key challenge. How do we stop sentence piece from splitting these clusters apart? We know that while a tokenizer might aggressively split a sequence of characters, it can never divide a single Unicode code point. So we map every valid cluster to a single unused character in the Unicode private use area, or PUA. We then feed those PUA characters into standard sentence piece. It does its normal statistical merging and outputs its token IDs. But because it is operating on our mapped symbols, the underlying orthography is mathematically shielded. By ensuring one PUA symbol equals one indivisible cluster, we enforced our type level guarantees at runtime without needing to rewrite the tokenizer. For our final technical slide, let's look at the KPIs. In the machine learning world, the ultimate test of quality is a metric called perplexity, which is essentially how confused the model is when predicting new text. Lower is better. Now, there is a small cost to our approach. Because we strictly enforce our type boundaries, we occasionally prevent the tokenizer from making aggressive text merges. As a result, we consume about 9 to 13% more tokens per sentence. But look at the payoff on the left. Because every single token is now a linguistically meaningful unit, the language model learns much more efficiently. Perplexity drops by 42 to 49% across Unigram and BPE architectures. The takeaway here is simple. Correct by construction code does its job exceptionally well. By enforcing type theoretic rules at the tokenizer level, we didn't just fix a text rendering bug, we made the downstream language model significantly smarter. To wrap up, standard tokenizers operate under the dangerous illusion that they are just splitting bytes. But when you look at complex writing systems through the lens of type theory, you realize you're splitting structured text. We uncovered a hidden assumption in modern NLP, which is that token concatenation is always total. By formalizing Brahmic orthography as a partial semigroup, we derived a repair that is formally safe and lossless. And by enforcing those types at runtime, we proved that getting your abstractions right doesn't just eliminate rendering bugs, it builds fundamentally smarter language models. Thank you all for your time, and thanks to the TyDe workshop organizers for helping us with everything. Our ACTA formalization and artifacts are available on GitHub, and we would be happy to take any questions.